Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In today's episode, we shall deal with optimization problem of a continuous function when the constraints are imposed on variables. That is, we are interested in solving a nonlinear programming problem which consists of an objective function with a set of constraints. In particular, in this episode, we are dealing with a NLPP with equality constraints. For that, let us consider the simplest form of a NLPP, which means a NLPP consisting of 2 variables x1, x2 and a equality constraints. For that, consider the NLPP which is either maximize or minimize the objective function z in terms of 2 variables f of x1, x2 subject to the constraints g of x1, x2 is c, where c is a constant, and obviously the decision variable x1, x2 greater than or equal to 0. So, a NLPP of 2 variables and a equality constraints are considered now. Optimize z equal to f of x1, x2 subject to the constraint g of x1, x2 equal to c and x1, x2 greater than or equal to 0. Here c is a constant. Now, how to optimize such a NLPP problem, which we are going to discuss in details. For that, first we think about the necessary condition for solving a NLPP. For that, first we rewrite the given NLPP in a particular form. Now, please make note of that. Here the objective function f of x1, x2 are continuously differentiable and g of x1, x2 functions are differentiable functions. Now, from the NLPP, I will write a differentiable function h of x1, x2, where h of x1, x2 is g of x1, x2 minus c. This function is differentiable with respect to x1 and x2. So, from the given LPP, from this equality constraint, we are obtaining a equation h of x1, x2, which is nothing but g of x1, x2 minus c. So, with this thing, the given LPP can be written as maximize or minimize, that means optimize z equal to f of x1, x2 subject to the constraints h of x1, x2 equal to 0, where x1, x2 are non-negative. So, the given nonlinear programming problem in terms of 2 variable and an equality constraint can be written this form. From this NLPP, now we try to obtain the necessary condition to get the maximum or minimum value of this NLPP. In order to get the maximum or minimum of the objective functions, now we have to form a new function which we called as Lagrangian function in terms of Lagrangian multipliers. From the given NLPP, the new function Lagrangian function is formed as L of x1, x2 lambda equal to f of x1, x2 minus lambda into h of x1, x2. Here this lambda is an unknown constant which we called as Lagrangian multiplier. So, from the given NLPP, from the objective function f and the function h of x1 x2, now in order to obtain the necessary condition, we have to construct a Lagrangian function. That Lagrangian function can be written as in terms of this equation, L of x1 x2 lambda equal to f of x1 x2 minus lambda of h of x1 x2. Now, from this Lagrangian function, now we try to obtain the necessary conditions. The necessary conditions for maximum or minimum value of the function f of x1 x2 subject to the constraint h of x1 x2 equal to 0 is given by dou L by dou x1 equal to 0, dou L by dou x2 equal to 0, dou L by dou lambda equal to 0. So, for the given NLPP, the maximum or minimum value of the objective function f of x1 comma x2 subject to the constraints h of x1 x2 equal to 0 is given as dou L by dou x1 equal to 0, dou L by dou x2 equal to 0 and dou L by dou lambda equal to 0. Now, this necessary condition can be rewritten in the following form. So, for a given NLPP, our Lagrangian function is this one, L of x1 x2 comma lambda equal to f of x1 comma x2 minus lambda into h of x1 comma x2. From this Lagrangian function, we obtain the necessary condition as dou L by dou x1 equal to 0, dou L by dou x2 equal to 0, dou L by dou lambda equal to 0. Those necessary condition can be written in this short form. So, the necessary condition is dou L by dou x1, which is nothing but dou f by dou x1 minus lambda into dou h by dou x1. The second condition is dou L by dou x2 equal to dou f by dou x2 minus lambda into dou h by dou x2. The third condition is dou L by dou lambda equal to 0. Therefore, dou L by dou lambda, which is nothing but minus of h of x1 comma x2 equal to 0. So, for a given NLPP, the necessary condition is given as dou L by dou x1 equal to this one, dou L by dou x2 equal to this one, dou L by dou lambda equal to this one. These three equations in short form can be written as L1 equal to f1 minus lambda into h1, and this equation is written as L2 equal to f2 minus lambda into h2, and the third equation dou L by dou lambda equal to minus h of x1 x2 equal to 0 is written as L lambda equal to minus h. So, for a given nonlinear programming problem, the in order to get the optimum value, the necessary condition is L1 equal to f1 minus lambda h1, L2 equal to f2 minus lambda h2, L lambda equal to minus h. Now, these three equations in a simplest form can be written as f1 equal to lambda h1, f2 equal to lambda h2 and minus h equal to 0. So, in order to get the optimum value of the given nonlinear programming problem, if we find f1 equal to lambda h1 and f2 equal to lambda h2 and minus h equal to 0 and solving these three equations, we will get the optimum value of the given NLPP. So, now with this idea, now we try to solve a nonlinear programming problem with equality constraints. The first problem is obtain the necessary condition for optimum solution of the nonlinear programming problem minimum z equal to f of x1 x2 equal to 3 into e power 2 x1 plus 1 plus 2 into e power x2 plus 5 subject to the constraints x1 plus x2 equal to 7. Of course, the decision variable x1 x2 are non-negative. So, the given nonlinear programming problem is a NLPP involving two decision variable x1 and x2 with a one equality constraints x1 plus x2 equal to 7. For this NLPP, we are interested in finding the necessary conditions. So, in order to solve the necessary condition for the given NLPP, our first idea is to obtain the Lagrangian function for the given problem. So, for the given problem, first we will find the Lagrangian function which is nothing but L of x1 x2 or lambda equal to f of x1 x2 minus lambda into h of x1 x2. For the given NLPP, the Lagrangian function is L of x1 x2 lambda equal to, our objective function is 3 e power 2 x1 plus 1 plus 2 e power x2 plus 5 minus lambda into, our h of x1 x2 for this problem is x1 plus x2 minus 7 equal to 0. So, for the given NLPP, we construct the Lagrangian function as 3 e power 2 x1 plus 1 plus 2 e power x2 plus 5 minus lambda into x1 plus x2 minus 7. Now, the necessary condition for this NLPP is f1 equal to lambda h1. That means, dou f by dou x1 equal to lambda into dou h by dou x1. So, this equation gives us, now differentiating this function with respect to x1, we will get 6 e power 2 x1 plus 1 minus lambda equal to 0. Next, the second necessary condition is f2 equal to lambda h2, which gives us, by differentiating this function with respect to x, we have 2 e power x2 plus 5 minus lambda equal to 0. The third condition is minus h of x equal to 0. So, minus h of x1 comma x2 equal to 0, which gives us minus of x1 plus x2 minus 7 equal to 0. So, the necessary condition for the given NLPP gives us 6 e power 2 x1 plus 1 minus lambda equal to 0, 2 e power x2 plus 5 minus lambda equal to 0, minus of x1 plus x2 equal to 7. Now, from the first equation, the lambda value equal to 6 into e power 2 x1 plus 1. Now, from the second equation, our lambda value is 2 e power x2 plus 5. Now, from the third equation, we will get x1 plus x2 equal to 7. From this, our x2 equal to 7 minus x1. Now, we name it as equation 1, this is 2 and this is 3. Now, from the equation 1, both sides of equation, left hand side of equation 1 and 2 is lambda. Therefore, from equation 1 and 2, we have 6 e power 2 x1 plus 1 equal to 2 e power x2 plus 5. Now, we cancel this 2 and this 6, we have 3 e power 2 x1 plus 1 equal to e power x2 plus 5. Now, by taking logarithm on both sides of this equation, we are getting the value of log 3 plus 2 x1 plus 1 equal to x2 plus 5. So, from the equation 1 and 2, we get the equation as 3 e power 2 x1 plus 1 equal to e power x2 plus 5. By taking logarithm on both sides, we get the value as log 3 plus 2 x1 plus 1 equal to x2 plus 5. Now, by making use of equation 3 in this equation becomes log 3 plus 2 x1 plus 1 equal to, now instead of x2, I will substitute the value 7 minus x1 from equation 3, therefore, 7 minus x1 plus 5. So, from this equation, we get the value of x1 as, if we take this x1 this sides, if we take this x1 to this sides, we have x1 equal to 1 by 3 into 11 minus log 3. So, by simplifying this equation, we will get our x1 value equal to 1 by 3 into 11 minus log 3. Now, by substituting this x1 in this equation 3, we get the value of x2 as 7 minus 1 by 3 into 11 minus log 3. So, the given NLPP, the optimum value is x1 equal to 1 by 3 into 11 minus log 3 and x2 equal to 7 minus 1 by 3 into 11 minus log 3. For this x1, x2, our NLPP optimize the Z. Let us have a break. Welcome back. Before break, we discussed about the necessary condition for solving a NLPP with an equality constraints, and we derived the necessary condition for the given NLPP with equality constraint as f1 equal to lambda h1, f2 equal to lambda h2 and minus of h equal to 0. With this necessary condition, now we try to solve a problem. The problem is a manufacturing concern produces a product consisting of two raw materials A1 and A2. So, the manufacturing concern produces product consist of two raw materials A1 and A2. The production function is estimated as Z equal to f of x1 x2 is 3.6 x1 minus 0.4 x1 squared plus 1.6 x2 minus 0.2 x2 squared, where Z represents the quantity in tons of the product produced and x1 and x2 designated the input amounts of the raw materials A1, A2. The company has 50,000 to spend on this raw materials. The unit price of the raw material A1 is 10,000 and the unit price of the raw material A2 is 5,000. Now, the question is determine how much input amounts of A1 and A2 be decided so as to maximize the production cost. So, the given problem is a business concern has an objective function Z which is given in terms of x1, x2 two variables, and the raw materials, there are two raw materials A1 and A2. For raw material there are budget constraints is there. With respect to that constraints, we have to determine how much inputs amount of A1 and A2 be decided so as to maximize the profit. So, first we will try to construct the NL nonlinear programming problem from this given problem. The given problem consisting a budget constraint. What is that constraint is the company has to spend maximum 50,000 for that raw material. Therefore, the constraint should be of less than or equal to 50,000. For A1, we are spending rupees 10,000 for that raw material. Therefore, the constraint, first constraint is 10,000 x1, and for the raw material A2, we are spending 5,000. So, 5,000 x2. So, the constraint restrict on this problem is 10,000 x1 plus 5,000 x2 less than or equal to 50,000, which we simply write it as 2 x1 plus x2 less than or equal to 10. Of course, the quantity of the raw material is always non-negative, therefore, x1 x2 greater than or equal to 0. So, the constraint of the given problem is 2 x1 plus x2 less than or equal to 0. From the given problem, it is clear that whatever be the money earned by the company, they should spend for the business. Therefore, we can restrict this inequality sign from this constraints. Therefore, this inequality constraints becomes equality constraints, which we rewrite it as 2 x1 plus x2 equal to 10. So, the given problem has an objective function Z with respect to the constraints 2 x1 plus x2 equal to 10, where x1 comma x2 greater than or equal to 0. Therefore, the given NLPP can be written as maximize Z equal to 3.6 x1 minus 0.4 x1 square plus 1.6 x2 minus 0.2 x2 squared. So, our aim is to maximize this objective function subject to the constraints 2x1 plus x2 equal to 10, x1 comma x2 greater than or equal to 0. So, the NLPP for the given problem is this one, which consisting of two variables x1 and x2 and an equality constraints 2x1 plus x2 equal to 10, x1 comma x2 greater than 0. So, in order to maximize the production output, we make use of the necessary conditions, which is nothing but f1 equal to lambda h1, f2 equal to lambda h2 and minus of h equal to 0. With the help of that necessary condition, now we try to solve this NLPP. So, in order to solve this NLPP, first we have to consider the Lagrangian function L of x1 x2 lambda, which is nothing but f of x1 x2. For our problem, f of x1 x2 is 3.6 x1 minus 0.4 x1 square plus 1.6 x2 minus 0.2 x2 square. This is our f of x1 x2 minus lambda into our h of x1 x2 is 2x1 plus x2 minus 10. So, for the given nonlinear programming problem, the Lagrangian function in terms of Lagrangian multiple lambda is 3.6 x1 minus 0.4 x1 square plus 1.6 x2 minus 0.2 x2 square minus lambda into 2x1 plus x2 minus 10. Now, we will make use of the necessary condition f1 equal to lambda h1, which gives us from this equation f1 equal to lambda h1 implies as 3.6 minus 0.8 x1 minus 2 lambda equal to 0. And the second condition f2 equal to lambda h2 implies 1.6 minus 0.4 x2 minus lambda equal to 0. And the third condition minus h of x1 x2 equal to 0 implies as minus of 2x1 plus x2 minus 10 equal to 0. So, by making use of this necessary condition, we will get these three equations. We name it as equation 1, 2, 3. Now, by solving this equation 1, 2, 3, we can get the values of x1, x2. Those three equations now can be rewritten as 3.6 minus 0.8 x1 equal to 2 lambda, and second equation 1.6 minus 0.4 x2 equal to lambda, and the third equation 2x1 plus x2 equal to 10. Now, from the first equation we have lambda value equal to 1.8 minus 0.4 x1. We name it as equation 4. From equation 2 and 4 we have 1.6 minus 0.4 x2 equal to 1.8 minus 0.4 x1. Now, by simplifying this equation, we have 0.4 x1 minus 0.4 x2 minus 0.2 equal to 0. So, by simplifying this equation, we have this equation, we name it as 5. Now, by making use of equation 3 in 5, we have the value of x2 equal to 10 minus 2 x1. Therefore, equation 5 becomes 0.4 x1 minus 0.4 into, instead of x2 we substitute 10 minus 2 x1 minus 0.2 equal to 0. Now, by simplifying this equation, we will get the value of x1 as 3.5. By solving this equation, we will get the value of x1 as 3.5. Now, by substituting this x1 value in this equation 3, which gives us x2 equal to 10 minus 2 into 3.5, which is gives us 10 minus 7 which is 3. So, for this NLPP the optimum value x1 equal to 3.5 and x2 value equal to 3. So, with this value of x1 x2 our objective functions gives the maximum value. Let me recap. For a given NLPP with respect to inequality constraints, in order to get the necessary condition, first we have to construct a Lagrangian function which we name it as L of x1 comma x2 lambda, where L of x1 x2 lambda equal to f of x1 x2 minus lambda into h of x1 x2. The necessary condition for maximum or minimum of f of x1 x2 subject to the constraint h of x1 x2 equal to 0 is dou L by dou x1 equal to 0, dou L by dou x2 equal to 0 and dou L by dou lambda equal to 0. Now, the question is obtain the necessary condition for the optimum solution of the following problem. The objective function is z equal to x1 square plus x2 square plus x3 square in terms of 3 variable subject to the constraints 4x1 plus x2 square plus 2x3 equal to 14. Thank you.